Problem number 14. A small block is released from rest on the rim of a fixed, frictionless hemispherical ball. From the time the block is released until it reaches the bottom of the ball, which of the following is true? First, the speed of the block never decreases. Second, the magnitude of the horizontal component of the velocity of the block never decreases. Third, the magnitude of the vertical component of the velocity of the block never decreases. Solution for problem number 14. Choice 1 is true because the block is never moving upward, so its potential energy never increases. Choice 2 is true because the only horizontal force the block experiences is the horizontal component of the normal force, which never points to the left. And choice 3 isn't true because the vertical velocity starts at 0 and ends at 0, so its magnitude must increase and then decrease. So it means that correct answer is C. First and the second are true, and that was a solution for problem number 14. Problem number 15. An egg is launched with a speed v from the ground, a distance d from a vertical wall. If v is high enough for the egg to hit the wall, which of the following could describe the angle theta that maximizes the height h at which the egg hits the wall? Solution for problem number 15. This problem is meant to be solved with limiting cases. When v going to infinity, theta going to 90 degrees. This rules out choices A and E. When v square equals gd, it is just barely possible to hit the wall at all, and the projectile must be launched at angle theta equal 45 degrees to do this. This rules out choices C and D, leaving choice B. We have other way to solve this problem directly. For that we need to write kinematic equations for distance and height. That will be these two expressions. From the first equation we can find what is time t and put this time to a second expression. So we have a height equal this expression, which is a function of angle theta. Now to find what is the maximum of this height, we need to take first derivative by theta and equalize it to 0. That will be this expression. And from here we can easily find what is tangent theta. We have tangent theta equal v square over gd. That's answer B, and that was solution for problem number 15. Problem number 16. A hexagonal pencil of a uniform density lies at rest on a horizontal table. It is pushed horizontally with a steadily increasing force halfway up its height as shown. What is the minimum value of the coefficient of static friction between the floor and pencil, so that the pencil will eventually begin to roll? Solution for problem number 16. If the pencil is about to start rolling, the normal force on it will be concentrated at the far end of the pencil. Taking torques about this point, the torque of the applied force must balance the torque due to gravity. If the pencil has a side length r, then this implies equation mg multiplied by r over 2 equal fr multiplied by sine 60 degrees, which will give us force F equal 1 over root 3 multiplied by mg. From other hand, for the pencil to be able to roll, the pencil must not be slipping at this point, which implies force F less than mu static multiplied by mg, and this both giving us mu static greater than 1 over root 3. This is answer D, and that was solution for problem number 16. Problem number 17. A thin rod has a non-uniform density. It is mounted on an axle passing perpendicular to it through its center of mass as shown, and is then rotated about the axle. The axle divided the rod into two parts, one on each side of it. Which of the following must be true, no matter how the mass in the rod is distributed? Solution for problem number 17. For simplicity, let's suppose the rod is made of discrete masses. So the reasoning is exactly the same if the rod is continuous. By the definition of the center of mass, if Ri is the distance of mass Mi from the center of mass, then we have next relation between left and right. The total mass will be next expression. Momentum will be this expression. Angular momentum will be this expression. And the kinetic energy will be this expression. If we look at these expressions, only the momentum P has the same sum of the same form. So the magnitudes of the momenta are equal, and in general none of the other quantities are equal. It means that the correct answer is B. The magnitudes of the momenta of the two parts are equal. That was a solution for problem number 17.